Okay. Okay, thank you very much for the sorry, can you also give me a 5-minute warning or something like that? Because I don't see a timer here. Okay. So thank you very much for the invitation. Sorry not to be there. I couldn't even come anyway since I COVID for, I don't know, the 4th time. So the organizer asked me to talk about the nuclear equation state and multi-messenger astronomy. And this is, of course, a very vast topic, which I'm not going to tackle in its complexity, in this full complexity, and all the details, of course. I will mostly focus of, well, my work and the work of my group, and I will mostly focus on what we have learned from this observation of binary neutron star, which of course you all know about. So essentially I want to reduce a bit the scope of the talk by saying what we are doing, which is trying to model from first principle the dynamics and of course the emission of these binary neutron stars in order to get to be able to interpret the observation and to get an idea of how we could constrain this neutron star equation of state. So let me jump in immediately in one of these very early results that we have published in 2017 when there was a lot of enthusiasm for it and so on. And let me explain this. So the main, this is a main possibility to constrain the nuclear equation state using binary observation and assuming that you have both a gravitational wave and a kilonova observation. And the main plot, what is showing is the constraint of the this lambda tilde parameter, which is called reduced tidal parameter, is the leading order contribution to tidal effect that finishes in the dynamics and the waveform, and as a function of the binary mass ratio. So what we have tried to argue here in this work was that essentially, if you look top right at the posteriors of the gravitational wave, what we had at the time for this particular observation was basically an upper limit. So we could say that this lambda tilde could be constrained to, I don't know, the value of 800 up to a few sigma. And this, of course, gives you this upper constraint in the main plot. But then what one could also argue is, and say is as well, there is this electromagnetic observation because of some energetics and feature of this electromagnetic emission. Then we, or many people argue that there should have been a remnant disk into the system generating this type of emission. That's, I think, now widespread conclusions. Many people agree on that. And then if you look at numerical relativity simulation, and that's of course one of the key points that interests, I think, everyone here in the audience, you discover that roughly the mass of the disk of the remnant correlates with this lambda tilde parameter. So the fact that you have certain energy emitted in the electromagnetic channel basically gives you through this numerical relativity relation a lower limit in the main plot here. And so this was a qualitative, if you want, semi-qualitative argument to say, well, in the end, we can constrain rather well this lambda tilde parameter, which is directly related and directly determined from the equation of state. And there is, can you see the slide, or is it broken also for you?
It looks like we see half.
It looks like?
We see half the slide.
We see half the slide.
Okay, so I don't know why it's completely broken for me. So I'm sorry for that. Yeah, I hope that other slide will not be like this, although they look like. So let's say this idea has been actually developed So I guess the only plot that you see here is a posterior plot, which is fortunately the relevant one. So essentially, yeah, we have developed this idea, and we have decided, considering a Bayesian analysis of gravitational wave, we have also considered Bayesian analysis of kilonova light course using semi-analytical models. And we have done, full Bayesian inference of that with model selection. So in particular, this model allows you to, consider kilonova light course from multi-component ejecta, means you have different type of ejecta mechanism, as you would expect from what we know and from our simulations. We consider isotropic and anisotropic models, and so on and so forth. And indeed, we have been able, using this type of analysis, to do the thing that is, qualitatively discussed in the previous slide before, in a fully Bayesian way. And so the plot that is missing, and I will send you the slide later, basically makes this proposal in a full Bayesian way. So the byproduct of this analysis was that we could compare the inference using different models, and the main conclusion there by this comparison was that in order to explain the particular kilonova with the particular model that we've used, we needed to use multi-component and anisotropic models, in the sense that they were preferred from, say, single component or two component with spherical geometry. And this is somehow interesting result because it is in agreement with what we see in numerical relativity simulation. Again, another broken slide, but again, one of the key plot is fortunately visible. What you can do at this point is to say, well, I want to see what the actual, besides calculating the posteriors and besides constraining this lambda tilde parameter, what you can do is to say, well, I can try to constrain the actual mass radius diagram of cold neutron star equilibrium. So what you see in this plot is that particular constraint. You consider a large number of sequences of TUV, Tolman-Oppenheimer Volkoff stars calculated with different equation state. And within this large subset, with this large set, you can select subset based on the constraint that you have from the gravitational wave. That's the gray, actually. And the constraint that you have once you select, once you also include the analysis of the kilonova, and that would be the blue shaded area within the gray. And additionally, of course, there exist other measurements. So recently there has been this nicer analysis, which you can also fold into this type of plot. And so if you do it, you get with a combined analysis that selected this green area actually within the gray, and that might give you, for example, an estimate of what is our now best chance or best estimate for the radius of a neutron star of mass 1.4 solar masses. So this turns out to be around 12 kilometers with an uncertainty of plus minus 0.7. In the plot that you don't see, but again is reported in this paper, you have seen similar results obtained over the years and by different groups, also using different techniques. But this seems to broadly agree to this 12 kilometer, which is apparently what these observations and latest theoretical results nowadays suggest. So this was just a brief introduction, if you want, to the problem and methodologies that have been recently applied. And here, what I wanted to stress, especially for this audience, is that some of these results are really obtained thanks to numerical relativity, and I think this is my summary slide on numerical relativity, which I can skip since many of you know very well the matter. And in particular, thanks also to public release of data and codes, of course, this is what we have used, what we have produced in Vienna and elsewhere as a computational relativity collaboration. There's a very large database with, I think now it's up to 800 data set with waveform, multipolar waveform from very, very different binaries with different orbit, with different masses, different equational state, and so on. This is all public, and you can download it from our GitHub. There are there is also software that is released to ease the download and the use of the things. And in parallel to that, we have also periodically released, and we are periodically releasing other type of data, like, for example, dynamical ejecta data, so the full profile of dynamical ejecta, for instance, for this work, other type of ejecta data, and also posteriors and things like that. And this can all be found in this Zenodo community. It's called NRGW Open Data, which you are also welcome to post stuff there and include. So many of these analysis that I'm going to present, and many of the results that I'm going to present are based on this data. Another picture that I might be able to skip is this. I think this is what we think nowadays is the the big pictures of the merger process for two neutron stars. The thing that I want to stress here is that there are very different timescales in the problem, timescales of emission, and we will discuss some of those during the talk. There are also, for what concern more electromagnetic emission, that there are also different ejecta. When people talk about kilonova, they talk often about ejecta, and but there's not one ejecta or just two, right? Like some simplified model kind of claims. If you really look into your simulations, what you see is that there's more very different processes that one after the other somehow produce the total amount of ejecta from the dynamical, from various type of winds. That of course have time scales that are very, very different along the ambient evolution. So this is something to keep in mind, I think, when one tries to model and interpret the data. So I will now discuss in the probably next 5 or 10 slides one particular aspect, that's the aspect of the gravitational wave, and then if there's time, I will say also something about electromagnetic counterpart. So these are the questions that we want to address. So the early part from this spiral, this merger, early part of the in the post-merger phase, early part of the evolution is mostly driven by the gravitational wave, and so that's what we could call the gravitational wave driven phase from a spiral to tens of milliseconds after merger. That's where all the gravitational waves are emitted. And for us modelers, for us theorists, few questions that we ask ourselves are how to obtain complete spectrum models. So from very low frequency, arbitrarily low frequency, to say kilohertz frequencies, how we can infer the equation state information from an observation of such a spectrum, and if our models are sufficiently accurate to extract information at all. So to start to answer some of this question, let me go again back to our event. Let me try to move. Sorry, I have something here. Okay.
Sebastiano, you muted yourself.
Sorry. Now can you hear me?
Yes.
Okay. So let me discuss the inference of the tidal parameter that we have seen in this introductory slide before. This measurement is challenging for a number of reasons. So they are all mostly related to this squeezed diagram, probably. This is supposed to tell where the information is as a function of frequency. And so you see that you have this chirp mass red line, which is mostly determined, let's say, a low frequency. We know this from post-Newtonian theory, but you say also that there's a solid line that is kind of unrelated to the other, and as its maximum at very large frequencies, if it has a maximum at all. So that's the curve that tells you from Fisher from information theory, that tells you where the tidal information is. And as you expect, the information on tides is just, at very high frequency. When the stars are about to touch, when the stars are merging, that's where when the most of the information for the tidal effects is present. So just physically just says that tides are short range short range interaction. So that's where the difficulty comes from, because not only you have to detect the signal at high frequency, you also have necessarily to model a gravitational wave until those frequency properly. And that's you go away progressively away from the post-Newtonian regime, you go in the strong field regime, and so it's the most complicated part to do in some sense when you try to model the two-body problem. For the particular results that, so we have revisited the analysis. There's a very detailed paper by Rossella Gamba, who's linked here. You can read all the details there. And we have revisited this analysis by looking systematically at all the possible approximant that are available, by looking at differences among these waveform approximate, by looking at Fisher matrix analysis and full Bayesian parameter estimation runs. And here is somehow one of the results that indicates that if you look carefully at the data, there is some systematics already in the measurement of 170817. So it's small, it is not a dominating effect, but you see that these lines are, or these posteriors for this particular parameter are, all a bit different from each other. And the nice thing is that we understand this, so this can be understood in terms of how the different approximates are built. The other nice thing is that fortunately these are not dominant, and if you look again at this estimate from this posterior of the radius, this is more or less compatible from all the different approximates. But the lesson is that in the future, especially, one has to be very careful and with waveform systematics, especially with this high SNR signal. One thing that we have done in this analysis in particular was to cut it to 1 kilohertz, which on one end means to minimize the information with respect to the standard 2 kilohertz analysis. But on the other hand, this limitation, this cutoff of the data allowed us to remove bimodalities in the posteriors, and made all the approximate that we explored, that we thought more compatible with each other, and so minimize these systematic effects. And you see there's quite a big effect between this gray 2 kilohertz analysis and the others. This is something that has been also noticed by other authors for this particular event. So this is another finding of this work. This is a somewhat difficult plot, but as the x-axis is the SNR, and the y-axis instead tells you essentially, it's a ratio that tells you essentially the deviation between the systematic error and the statistical error. So essentially, when you are beyond, say, 0.5 or 1, you are making a systematic error in each of this line. You are making a systematic error that is of the order of the statistic error or beyond. And this is done for several this is done for several approximates, sorry. As you can see, it indicates these are all the state-of-the-art approximates that are available for analysis. And as you can see, it indicates that as soon as you go, beyond 80 or 100, SNR of 80 or 100, then the measurement will become totally dominated by the systematic. So this is in some sense a warning that says, look, if you have a very large SNR event today, well, what you will be measuring in terms of tides is systematics. Or if you want to think about Einstein telescope, well, you need to significantly improve your gravitational wave approximate in order to extract the physics that we promise typically for Einstein telescope. Then the obvious question is to say, okay, but can I use just numerical relativity waveform, right, instead of one of these approximate? So we have also tested that. We have also looked into some of this large database, which contains some very high resolution runs that are convergent and so on and so forth. And we have done also similar analysis there. This is summarized in this table. I don't want to give you all the details, but it's essentially a faithfulness analysis and as a function of SNR. And what this tells you is that, again, every time there is X, it means that this particular numerical relativity waveform is not sufficiently accurate to probably to make a parameter estimation at that SNR. And you see that as soon as you reach this threshold of 80, essentially most of the data is not fine. So this motivated us as a numerical relativist to investigate better and improve our methods, and that's one of the projects that we have done in this direction. I switched something a bit more technical, but I think you can follow this. So one of the main reasons for this low unfaithfulness of this numerical relativity data is actually the hydrodynamic scheme. So you do want to capture some of this complex hydrodynamics flow and pattern, but at the same time you want to keep the convergence of your codes sufficiently high. So to try to meet these two requirements, what we have explored is an entropy flux scheme. So it's something very simple actually. There's your hydrodynamical fluxes will be composed by two parts. Let's call it a lower order part and a higher order part. In our case, they are all high order, but one is a limited flux. So there's a limiting procedure in the reconstruction of the variable, let's say, and one is an unlimited. So something that in principle gives you oscillation, and then you simply combine them linearly. And the key thing is of course what we use to combine them. And in this particular case, what we decided to use, also based on previous work, was to use the entropy residual. So there is an equation for the entropy. The residual has to be 0. As soon as the residual is sort of violated, so away from 0, potentially very large, then this is an indication that that part, those grid points are for example, a shock, or for example, the surface of the star. It doesn't really physically distinguish, of course, between these two things, the method, but that's what seems, but it seems to work quite nice. So the pictures you see on one side, you see the 3 snapshot from the evolution, and on one side you see, say, the density, and on the other side you see this entropy residual, and you see that it is 0 everywhere essentially, except that when the stars are orbiting, it captures the surface of the star. When the stars are touching, it captures this shearing interface of the star, and while remaining 0 elsewhere, and it captures even this spiral arms, and then of course the ejecta and so on very nicely. Everywhere where this entropy residual is 0, it means that you are using effectively an unlimited scheme, so something like a high order finite difference scheme rather than a finite volume scheme. So this is one of the possibilities that we are exploring that we have developed and that we will further explore to obtain a highly convergent waveform. And it works in the sense that this waveform that you see are fourth order convergence. So there was a plot before, which of course squeezed like all the others. But it seems nicely working and to give the convergent waveform that may, in this case, at the previous resolution that we the resolution of the previous round that we considered, this will extend the faithfulness of the waveform up to this, up and a bit beyond this, limit of 1800, which of course we want to beat. We have done more work to try to, model the entire spectrum, the entire gravitational wave spectrum. Was there a question?
No question.
Okay, interrupt me if you have a question. We have done a bit more work to model the entire spectrum. So the main strategy here, and we have achieved this. The main strategy here is to combine an analytical model, in particular effective one-body model, that of course are valid up to the merger, with direct numerical relativity data. So what we do is to have a EOB model which is up to merger and has particular choices, implements particular choices that gives the best faithfulness using numerical relativity data, but without using directly this data. And then up to this, when this model finishes and it's not valid anymore, this is the merger, which of course it predicts the merger, but afterwards is not anymore valid. At that point, we attach a completion, pretty much what you do with binary black hole, where you have a EOB model and then you stick to it a ring down model. Here, the ring down model is actually a post-merger model inferred from all this large number of simulations, and this allows you to, build effectively an analytical model that is numerical relativity informed, and it includes all the frequencies in the spectrum. The particular way this is done, so how the numerical relativity data is synthesized, or into an analytical model, is actually by using equation state independent or sensitive relations. So we know that several quantities, up to some extent, they don't depend on the equation state if you use if you parameterize them through certain parameter, this tidal parameter. So in other terms, it's not true they don't depend on the equational state, but it's true that the tidal parameter captures perhaps to 1% the entire dependence of the equational state. So it's in this sense that we say that they are independent. And so we have fitted systematically from the database all this quantity, and then we have written down a couple of simple analytical models, either based, on sinusoids or wavelets. The most modern one uses wavelets to represent this complex emission after merger. And so with that, we can work and we can make prediction and say, for example, if we have Einstein telescope or any 3G detector, when can we detect actually post-merger? And so this is a Bayesian analysis of various binary based on the model, and they all seem to indicate that if the SNR in the post-merger, so after merger, is of the order of 7-8, then you can claim an actual detection, which is important for a number of reasons, because it tells you, well, first of all, that the remnant is not a black hole, but a neutron star remnant, and there are many applications of this. And this is in line with other type of analysis that instead of modeling the signal, they are morphological independent, and they simply try to look into power excess, for example. So at this level, the predictions are compatible. But of course, when you have a model, you can do something more. So you can go back and say, well, let's imagine that we do have such a detection. what this detection will tell us about the equation of state, which means for us, what this detection will tell us about the mass radius diagram. And here the plot shows again, this gray area is essentially, what I showed at the very beginning, the best, the best constraint that is available to 2020, based on those observations. And you may say, okay,
minutes.
Thank you. So I will do only this part of the talk. And you may ask yourself and say, look, I have the current constraint, and tomorrow I turn on the Einstein telescope, and I have one detection, which has the minimum SNR in the post-merger for a post-merger detection. So SNR in the post-merger will be something like 8. Of course, the SNR in the spiral will be huge, about, in this case, about order 100 or 200. So a really, really big signal. And let's also imagine that we don't have systematics. Then you see that, and you can ask, okay, what's the difference between detecting, in spiral only and full spectrum? And that's what the plot tells you. So if you make an spiral merger detection of this type, you will have a very tight constraint. It is the magenta from the spiral merger, which is 100. You see the gray area shrinks a lot just for one event. But you see also that, of course, the black one is the right signal, right? In this case, this is an injection. This is a fake mock experiment. But you see that this magenta area doesn't really capture the maximum mass of the real injection, of the real signal. And interestingly, if you just use the full spectrum, so if you can also measure the post-merger, you get this blue area. And this blue area mostly follow, it's much larger here, the posteriors, because post-merger doesn't tell you much about that, but it does tell you, and you do learn about the maximum mass, and in a correct way. So in this case, what we found out through this analysis is that you can constrain with just one detection at the minimum SNR, the maximum density, say, of the relative TOV, and the maximum mass of that sequences of TOV to 10%. Just using this quasi-universal relation that are built in the model. And interesting thing is that this 10% and so on is kind of the equivalent of what you get as an uncertainty in your universal relation. So in the universal relation from which the model is built from. So basically, you cannot do better than that. You do need to use a universal relation, but you cannot do better than that. So just one observation would give you this. An important technical aspect, if some of you is doing such a business, and that's very nicely included in this analysis, are these recalibration parameters. So you don't infer just for the parameter of the model, but you allow some parameter to fluctuate around their value by, say, other random variable, which you infer as well. And this is important because you know that your theoretical model has uncertainty, and with this recalibration parameter, you infer within that uncertainty, and you include and you fold in your theoretical uncertainty, for instance, in the equation of state insensitive relation and in your analysis. So this is what this is an interesting technical aspect. It gives a bit more conservative result, of course, but it allows you to fold your uncertainty also on the theoretical level within the statistical analysis. You can do something more, of course. You can wonder if there's a phase transition, or if there's new degrees of freedom that appears in the remnant. This is well possible from nuclear models. And you might wonder, okay, can I catch those? Okay. The answer is yes and no. Well, first of all, this type of effects are confined in a very small windows of binary parameters. They are US independent, and they are confined for for instance, for certain masses. And second of all, you can prove, of course, you can inject a signal and see that one signal gives you, with a phase transition, gives you a very fast collapse, whereas the other is very is stable, and so you can look at this type of things. But of course, in reality, you have to think that you don't know which is the right signal, right?
5 minutes.
Yeah, thank you. In reality, you have to think that you don't know what is this right signal. So as a proof of principle, you can show that these effects are detectable. Whether we will be able to detect them or not is another question, is much more complicated. And in some sense, you will also have some space for interpretations and opinions, which is not necessarily something good. Another thing is that what you typically measure here is the violation. So you do the inference with the model, which contains a quasi-universal relation. And then what you do, you measure a violation of this quasi-universal relation. But as we just commented, we know that this quasi-universal relation are not perfect. So on one end, one has to always try to include this recalibration parameter, which are critical here. And on the one end, there is a systematic bias also here, because of course your model is calibrated through numerical relativity, and so you have already made a choice in your simulation what to simulate, and then what data you have and use. So it's very, very delicate. Some of these things are discussed in this work. In the future, the interpretation will be, I think, very, very delicate. But well, it's good that there will be this possibility. And perhaps last comment here. What we have learned from this type of analysis is that it's not just that one parameter is violated. It's more that the template, if you want, tries to adapt to anything that tries to adapt the data. So it's not that you will see a softening or a phase transition just because the F2 versus kappa relation is violated. It's not necessarily like that. You could have that completely captured by your template and still have some bias, for instance, in the collapse time, which is something that is more complicated to extract from the simulation. So there are big disclaimer, there are big systematics in this type of analysis, and there's certainly need for more work before applying them. Yes, so let me try to conclude with the last two slides. So far, basically, I've indirectly assumed that the remnants are cold, is made of cold matter, say beta-equilibrated cold matter, which is of course completely wrong. It's not true. If you look at the snapshots, which probably you have seen, on the right, what you have is the thermodynamical state of the remnant in terms of temperature and density, or electron fraction and density. And so, as you know, there are temperature gradients that develop. The thing is not the matter is not in weak equilibrium, but you have neutrino emission, just changes the composition, and so on and so forth. So another question is, okay, can we detect some of this effect? Okay, we get information from the states of matter. And to try to answer this, this is work by Jacobs, Fielder, Penn State. We have made this experiment. We have run simulation with microphysical equation of state and different effective nuclear masses, which is the way the typical finite temperature effect are parameterized within this microphysical model. And different nuclear masses gives you different specific heat, and so they give.
You want to get questions?
Sure. Yes.
Great, that quick.
Okay.
Right. Thank you. Thanks, Sebastiano.
Okay. So I have no time.
Can I hear the answer to this slide, please? Just
Yes, sorry.
Things. Yeah.
It's breaking a bit. That's why. Is there a question or not?
Not sure.
No, you've been interrupted in the middle of trying to finish at least that slide, and I was wondering what was the final message.
Yes. So let me try to wrap up then. So yeah, different effective nuclear masses gives different specific energy, which means different thermal pressure. And in fact, we see different remnants with different compactnesses. And this is simply, strangely enough, this does not happen at very, very high density, by the way, but a little lower densities. And strangely enough, this is still reflected into, or surprisingly enough, this is still reflected into the gravitational wave, as you can see here on the right. And so the answer is that yes, in principle, instrument like Einstein telescope is sensitive even to this effect. And these are full Bayesian analysis recovered with a model similar to the previous one, but without imposing this quasi-universal relation. And you see that, for instance, the peak frequency, but many other quantities in the recovery are different, and indeed because the waveform are different. And so, yes, 3G will be sensitive to thermal effects in the remnant, although the same caveat that I mentioned before, of course, hold here. So when you have a real observation, a real signal, it will be incredibly complicated at the level of conceptual level, at the logical level, to claim that there's a detection of this and that, precisely because of the same reason as before.
Okay, thank you.
Yeah, I think I finished my time, or not?